Imagine looking at a lush green forest that is secretly just starving to death.
Right.
On the outside, there's, abundant light, there's plenty of water, and it looks like an absolute paradise.
Yeah, totally healthy.
Exactly. But if you zoom in, you realize the trees are essentially choking,
Yeah.
like completely unable to absorb a single nutrient from the soil around them.
Which is a terrifying thought.
It really is. And today, we are looking at a catastrophe exactly like that. But instead of a sprawling forest, this entire biological collapse is happening inside a glass box,
Right.
sitting right in the middle of a living room.
Yeah, so we are jumping into a microscopic resource war today. And the battlefield is a single, heavily compromised aquarium.
Right.
The dynamics playing out in this small volume of water are just a perfect real-time study in resource competition, compounding environmental stress, and systemic instability.
And it scales, right?
Oh, absolutely. The biological mechanics determining which organisms live and die in this tiny tank, they apply to systems of literally all sizes, from your backyard vegetable garden all the way up to, global agricultural supply chains.
That is wild. And that brings us to our mission for this deep dive. Our source material today is this highly detailed, honestly fascinating journal entry published on May 22, 2026.
Yeah, it's quite the read.
It really is. The author is an aquarist named Ang, and the post is titled Notes on Fishkeeping, Part 263.
Part 263.
Right. The fact that this is Part 263 tells you right away that we are dealing with someone who has been engaged in a relentless, ongoing process of observation.
Yeah, someone very dedicated.
So we are going to unpack how a massive algae bloom, a struggling little floating plant called Common Salvinia, and a single fish can teach us about the fragile, invisible balance of the environments we build.
Well, the environmental baseline is really where this entire narrative begins. The journal reveals a tank that is heavily infested with an algae bloom.
Heavily infested.
Yeah. For anyone who has ever kept an aquarium, you know what this looks like. The water turns into this cloudy green soup.
Ugh. Yes.
It coats the glass, it chokes out the decorations. I mean, visually, it is deeply unpleasant.
Right, and the human instinct in that moment is absolute panic mode.
Oh, for sure.
You want to immediately do a massive water change, scrub the glass until your arm hurts, pour in some, I don't know, chemical albicides.
Just forcefully restore order.
Exactly. You just want the water to look pretty again. But the journal details a highly conscious, deliberate choice to just leave the tank completely alone.
Yeah, Ang specifically designates this glass box as an observation tank.
And to manage this absolute mess, there is only one inhabitant left inside.
Just one.
A single polar parrot cichlid fish functioning as the tank's designated gardener.
Gardener in very big air quotes.
Right. This detail is just hilarious to me. This is like having a sprawling backyard completely overrun with 6-foot-tall aggressive weeds. And instead of renting a heavy-duty lawnmower or hiring a landscaping crew, you just drop a single bewildered sheep into the middle of it.
A single sheep.
Yeah. You just drop it in, grab a notebook, sit down on the patio, and watch what happens. Like, that sheep is not going to solve your weed problem.
No, it's really not. But what's fascinating here is this sheer restraint on display. I mean, it's actually the core of the scientific method.
Oh, how so?
Well, when you constantly intervene in a failing system, like adding a chemical here, changing the water there, scrubbing a surface, you introduce so many overlapping variables.
Oh, I see.
You can never be entirely sure what is actually causing the underlying problem.
Yeah.
You kind of lose the signal and the noise of your own interventions.
You literally muddy your own data because you're too busy playing lifeguard.
Exactly. Stepping back and letting the system run allows the ecosystem's unhindered response to stress to just play out in real time.
Right.
Observing that raw, unfiltered response provides empirical data you would never get if you constantly tried to curate and micromanage the environment.
It's hard to do, though.
It is. It requires immense patience and a real willingness to let things get visibly ugly, to truly understand the mechanics of the failure.
Well, let's look at the mechanics of that failure, because it is a brutal conflict. The Common Salvinia, which is a really neat little complex plant that floats right on the surface of the water, is losing badly.
Very badly.
The journal includes visual evidence showing the Salvinia undergoing severe cellular degradation.
Yeah, the photos are pretty striking.
They really are. The bright green chlorophyll is breaking down, leaving these sickly yellowing and browning leaves. The text basically outlines two immediate hypotheses for why the algae is defeating the Salvinia so soundly.
Right. So the first hypothesis is acute nutrient starvation.
Okay.
The algae are aggressively outcompeting the Salvinia, consuming the bulk of the available nitrogen and trace minerals in the water column. It's essentially leaving nothing behind for the complex plant to absorb.
Wow. And the second one?
The second hypothesis introduces physical blockage. The journal points to the possibility that the algae might actually be coating the Salvinia's microscopic root structures.
I'm stuck on one thing, though.
With that,
Well, floating plants like salvinia or duckweed usually absolutely dominate aquatic environments because they literally sit on top of the water.
right, they do.
They get first dibs on the atmospheric air above the tank, and they get first dibs on the light source. They hold the ultimate biological high ground.
They really do.
So how does a tiny, primitive, single-celled algae manage to beat a complex plant with that kind of massive tactical advantage?
It really comes down to the compounding nature of a biological attack. You see, algae does not play by the rules of complex plants.
How do you mean?
Well, it is primitive, which means it reproduces exponentially. It doesn't need to expend energy building intricate structures like hydrophobic leaves or specialized stems.
It just copies itself.
Exactly. It simply copies itself. When the conditions favor it, algae can explode in population practically overnight. It creates this massive biological sink, draining the nitrogen and minerals from the water way faster than the Salvinia's complex roots can process them.
So the salvinia is literally starving in what should be a buffet.
It's actually worse than just starvation.
Oh, no.
Yeah, because the algae is so pervasive in the water column, it acts almost like a physical sludge.
Ugh.
Roots do not just act as simple straws sucking up water. They are incredibly intricate structures that require direct, unimpeded contact with the water for nutrient uptake and, crucially, for gas exchange.
Okay, so they need to breathe, basically.
Right, so when the algae physically coats those microscopic root hairs, it forms an impenetrable biological barrier.
It is literally smothering the plant.
Exactly. The Salvinia cannot uptake whatever trace minerals happen to be left, and it cannot efficiently exchange gases.
Man.
It is a brilliant, devastating two-front war, starvation and suffocation occurring simultaneously.
That is terrifying. It's not just stealing the food off your plate. It is wrapping its hands around your throat at the very same time.
That's a dark way to put it, but yes.
But the journal doesn't stop at the biological attack. It looks beyond the algae and introduces a completely different vector of stress.
Right, the environment itself.
Yeah, there's an environmental factor supercharging this destruction.
The third hypothesis zeroes in on that, suggesting the plants might be suffering from extreme light burn.
Right. And the entry notes that the salvinia in other tanks throughout the house is thriving beautifully.
Do it just fine.
But this specific observation tank is positioned right in the center of a room, and importantly, it has been blasted with significantly higher levels of LED light over the past 3 days.
Which is a massive clue.
It really is. If you look closely at the metadata of the journal entry, there are some major clues hidden in the tags. The author tagged the post with circadian rhythms, continuous illumination, and photo period.
Interesting.
Yeah, which strongly hints that the light cycle in this sender room hasn't just been exceptionally bright. It has been drastically altered or possibly left on nonstop.
And see, assuming that more light automatically equals more growth represents a fundamental misunderstanding of how photosynthesis actually works.
Yeah, because as casual observers, we instinctively assume plants just want infinite light.
Right, more is better.
Exactly. Light is their food. We think of them like solar panels. If the sun is out, they are generating power and growing.
But it's not that simple.
No. This setup sounds like a human chugging 10 cups of coffee to be hyperproductive, only to end up jittery, burnt out, shaking at their desk, and totally unable to function.
That analogy is biologically spot on.
Oh, really?
Yeah, we often think of photosynthesis as a single uninterrupted light-driven event. But in reality, it is divided into two distinct phases.
Okay, break that down for me.
First, you have the light-dependent reactions, where the plant captures solar energy.
Like charging a battery.
Exactly. But then you have the light-independent reactions, frequently referred to as the dark cycle or the Calvin cycle.
The dark cycle.
Right. This is the crucial phase where the plant actually uses that stored solar energy to synthesize sugars and build cellular structures.
So they literally need the dark.
They do.
They have to rest to actually process all the energy they consumed all day.
They absolutely require a natural photoperiod, a regular, predictable cycle of light and dark to maintain their circadian rhythms.
That makes so much sense.
Continuous illumination forces the plant into a state of metabolic overdrive. It keeps absorbing solar energy, but without a resting period to process it, that energy actually becomes destructive.
It is burning the plant from the inside out.
Biologists call this photoinhibition. The plant is taking in so much energy that it begins producing free radicals that tear its own cellular machinery apart.
Wow.
And you have to layer these stressors together to see the full picture here.
Right, the compounding effect.
Exactly. The Salvinia is being forced to process an overwhelming toxic amount of light energy, but its roots are entirely smothered by algae, and the water has been stripped of the nitrogen it needs to build new cells.
It has no defense.
None. Giving a complex organism massive amounts of excess energy without the necessary chemical building blocks to process that energy results in severe cellular damage.
So those yellowing leaves aren't just hungry.
No, those yellowing leaves are not just starving. They are quite literally being destroyed by the light they rely on to live.
It is just a perfect storm of environmental hostility. You have an aggressive biological invasion from the algae, physical suffocation of the roots, and relentless toxic radiation from the continuous light.
It's bleak.
It really is. But the journal digs even deeper. The author ultimately deduces that the suffocated roots and the extreme light, while massive stressors, are still just symptoms.
It's the tip of the iceberg.
Yeah, they are the squeaky door hinge in a house that has a cracked foundation.
Right. What's fascinating here is that the author looks past the visible, localized damage and zeroes in on the invisible medium connecting every single element of this ecosystem.
The water itself.
Yes.
The journal suspects the core issue driving all of this chaos is the foundational water chemistry.
The baseline.
The entry notes that the water parameters are likely fluctuating rapidly. It points specifically to unstable pH and spiking ammonia levels as the true underlying culprits causing immense unnecessary stress to the plants.
And this is the vital paradigm shift in understanding systemic failure.
How so?
If the foundational environment is unstable, treating the visible symptoms is an exercise in futility.
I mean, if the water itself is broken, does anything else even matter?
No, really.
Like, can you even fight the algae or fix the lighting schedule if the pH is swinging wildly out of control?
You cannot. You will never cure the yellowing leaves or permanently eradicate an opportunistic infection like algae if the chemical baseline is chaotic.
It just keeps coming back.
Exactly. Take pH, for example. The pH level of water dictates the chemical availability of almost everything suspended in it.
Okay, I think I need an analogy for this one.
Sure. To understand this, imagine that nutrients like nitrogen and iron are tiny magnets floating in the water.
Okay, magnets, got it.
And the plant's roots use a specific electrical charge to attract and pull those magnets in.
So they literally pull their food to them.
Right. When the pH of the water swings wildly, the entire magnetic field of the water changes.
Oh, wow. So the plant physically loses its magnetic grip on its food?
Exactly.
Yeah.
The nutrients might be physically present in the water, floating right next to the roots, but the plant physically cannot absorb them because the chemical polarity is wrong.
That is wild.
This is known as nutrient lockout.
So even if the algae wasn't stealing the food, and even if the roots weren't smothered, the Salvinia might starve anyway simply because the water chemistry refuses to let it eat.
Exactly. And then you introduce ammonia spikes into that already chaotic environment.
Which is bad, I'm assuming.
Very bad. Ammonia is a highly toxic waste product generated by decomposing organic matter and fish waste.
Okay.
In a stable, mature aquarium, colonies of beneficial bacteria act as a biological filter. They process that toxic ammonia into less harmful nitrates.
Like a natural waste management system.
Right. But in a fluctuating, wildly unstable system, that delicate biological filter collapses, and ammonia builds up rapidly.
It essentially turns the water into a literal acid bath.
It does. Spiking ammonia chemically burns the delicate tissues of the plant roots. It creates a fundamentally hostile baseline.
Wow.
And this is the universal rule of ecology we are seeing play out in this tiny glass box. In chaotic, rapidly fluctuating environments, complex organisms will almost always lose to primitive, fast-adapting opportunists.
Because they're too specialized.
Yes. The Salvinia requires stability to maintain its intricate root systems, to manage its delicate circadian rhythms, and to process complex chemical bonds.
And the algae.
The algae, on the other hand, thrives on chaos. It can adapt instantly to a sudden spike in ammonia or a drastic change in light, utilizing those raw resources exponentially faster than the complex organism can even process what is happening.
So the algae is essentially acting as a biological disaster capitalist.
Disaster capitalist.
Yeah. It just waits for the infrastructure to collapse, moves in instantly, and completely takes over everything while the complex organisms are still trying to figure out why the pH changed.
That perfectly encapsulates the dynamic. The algae is a symptom of the broken infrastructure.
Which brings us to the author's conclusion. Moving forward, the journal notes a plan to experiment with various chemical or physical treatments to stabilize those baseline water parameters.
Which is the right move.
Yeah, there is a clear recognition that you cannot just reach in with a net and scoop out the algae or just turn down the lights.
Right, that's just treating symptoms.
Exactly. You have to fix the invisible water chemistry that is allowing the disaster capitalist to win in the first place.
Stabilizing the foundation is the only sustainable solution.
Right.
Once the pH is locked in and the ammonia is processed, the system can begin to organically regulate itself again. The complex plants can resume their natural dominance.
And that is the ultimate takeaway here for you, listening. When you are facing a highly visible, incredibly frustrating, localized problem, whether that is a persistent, unexplained bottleneck in a major project you are managing, or maybe a sudden breakdown in communication within your team.
Or even just a recurring point of friction in your own daily routine.
Exactly. You have to resist the overwhelming human urge to just violently scrub away the algae.
It's so tempting, though.
It is. But you have to check your invisible systemic water quality first. You have to ask yourself if the foundational parameters of your environment are truly stable, or if you are just endlessly treating the symptoms of a wildly fluctuating, chaotic ecosystem.
Shifting from reactive problem solving to systemic thinking really fundamentally changes how you approach failure.
It really does. But before we finish up this deep dive, there's one lingering detail in this journal entry that demands a closer look.
Oh yeah, the elephant in the room.
Because it raises a deeply complex question. We talked extensively about how this tank was deliberately left infested with algae to serve as an observation tank. We talked about how the author held back from intervening to gather raw data. And to manage that space, a single polar parrot cichlid was left inside to act as a gardener.
The lone sheep dropped into the overgrown backyard.
Exactly. But we just spent this entire conversation establishing that the core foundational issue of this tank isn't just unsightly algae or overly bright lights.
Right.
It is wildly fluctuating pH and spiking ammonia. We are talking about invisible, volatile water chemistry that is literally burning the complex cellular structures of a hardy floating plant.
Yeah, it's causing it to starve, suffocate, and melt away into the water column.
So about that ammonia.
Well, ammonia, as we detailed, is a corrosive waste product. It doesn't just burn plant roots.
Right.
It is highly toxic to fish gills.
Oh, man.
It chemically burns their respiratory tissue, severely restricting their ability to pull oxygen from the water.
So it's effectively suffocating them while damaging their external slime coat.
Exactly. It is an agonizing environment for a fish.
Which is why I want to leave you with a final, honestly, somewhat uncomfortable thought to ponder on your own after we wrap up here.
It's a tough one.
If the underlying conditions in this deliberate observation tank are chemically volatile and actively toxic enough to destroy the cellular machinery of complex plants,
Yeah.
what is the ethical line of keeping a living, breathing animal trapped inside that intentionally destabilized environment just to see how the experiment plays out?
Really makes you think.
When we step back, fold our hands, and choose to observe a failing system to gather pure data,
Yep.
who is actually paying the price for the knowledge we collect?